Alright, in this series we're going to be talking about how to solve, or how to design rather, a reverted gear train with multiple gear ratios, and we're going to achieve this using Python. First off, if you don't have a background with gear ratios, go look it up. This is just going to be brief. Basically, if we have two gears, gear A and B, and A has the motor connected to it, and then B is the one that's driven, then the gear ratio is going to be the number of teeth of B, or the output, over the number of teeth on the input, or the diameter of the output over the diameter of the input, and that equals the gear ratio. And with the gear ratio, you can convert the torque from A and figure out what amount of torque is on B. Similarly, you can get the speed, the RPMs of B, using the inverse of the gear ratio here. So as a quick example of that same one here, since we have 60 and 30 teeth, we have the output over the input, so our gear ratio is 1/2. So the torque on B is going to be the gear ratio 1/2 times the torque on A. So if we have 1,000 pound-inches or inch-pounds, doesn't really matter how you say it, then we're going to have 500 pound-inch over here. Similarly with the RPM, if we have a input RPM of 4,500, then 1 over 1/2 is just going to be 2, right? Because 1/2 goes into 1 twice, times the RPM of A, which is 9,000. So a reverted gear train is a gear train where the input shaft, so if you can imagine a motor connected to this shaft here, and this is the output shaft, a reverted gear train is where these two shafts are collinear, and they're parallel, so they're along the same axis, and then shaft 2, 3, which is called the counter shaft, is parallel to both of these. And the challenging thing about designing one of these is that the center distance between, so basically the diameter of 1 plus the diameter of 2 divided by 2 has to be equal to the diameter of 4 plus the diameter of 3 divided by 2. Which basically says that the center distance has to be equal to keep the shafts parallel. To calculate the gear ratio for a reverted gear train system like this, you need to multiply the two gear ratios together. So here, output is 2, input is 1, so we have output over input, N2 over N1 times D4 over D3, where D4 is the output and D3 is the input. Now I could have used N here in place of D, or D here in place of N. It doesn't matter because they're equal to each other, as I showed back here. Right here they're equal to each other, so you can use either one, it doesn't matter. And so that would be the overall gear ratio for a simple reverted gear train. Now, the whole purpose of what we are going to be doing in this series is designing a reverted gear train with multiple ratios, so basically multiple gears. Like in a 5-speed car, you have the 5 speeds. Those are all different gear ratios that your transmission can achieve. This is a simple setup for a 2-ratio reverted gear train. So you can see here that if we have a motor connected to the input shaft, which is this one right here, the way the gears are connected now, power would flow from 1 to 2, through the counter shaft, through 3, and then through 4, and then out the output shaft. And as you can see here, gears 5, 6, 7, and 8 are not engaged. But if they were engaged, 2 would engage over here to 5, and this counter shaft would slide over. 6 would engage with 7, so power would flow from 5 to 2, 6 to 7 to 8, and then out the output shaft. And we have this gear 7 here is important because this is an idler gear. With gears, as you can see here, they rotate in opposite direction. So we cannot get forward and reverse using a setup like this. We have to add another gear in between. By doing that, we can get the counter shaft and the output shaft to rotate in the same direction, and that's how we achieve reverse. So right here, the forward gear ratio is gonna be from N2 to N1, N4 to N3, right? So that's gonna give a 4.1 with this setup. If you look at the dimensions here, and they're kind of messed up, but if you look at the dimensions and do the math, you'll come to see that this is true. And then for reverse, it's similar, but instead we're doing 2 to 5, 7 to 6, and then 8 to 7. And if you notice here, the idler gear will actually not play any role in determining the gear ratio for the reverse gear. And that's because N7 will just cancel out. So what we actually just have is N8 over N6 right here. So that just tells us that the idler gear actually is just kind of there to reverse the power into a different direction, or the torque, or the speed, however you want to think of it. So it doesn't really come into play in the design procedure until we start talking about the center distance here and the stress considerations on this gear. Then we'll need to do some actual design here. But as far as simple design goes, we actually don't really need to worry about the idler gear because it just cancels out in the calculation. So with a problem like this, designing one of these is mainly when you're designing something like this, you're going to be given a target ratio. So this is actually a project that I did for class, and this was my final design, and I created this design using the optimization software in Python that I'm going to be demonstrating in the next couple of videos. So basically I was given these target ratios. I was given a 4.1 for the forward gear ratio. So basically means if we put in 1,000 pounds of torque over here, or inch-pounds, that on the output side of forward we would get 4,100 inch-pounds. Or in reverse, if we put 1,000 pounds in, then we would get 9,300 out. So that is one of the challenges first, is hitting those target ratios while maintaining the same center distance, while making sure that the gears aren't too big, and some of these other considerations I'll talk about here. Probably one of the hardest challenges is the diametral pitch constraint. Some people also call this the gear module. But basically the gear module is the ratio of teeth on the gear to the distance around the circumference of the gear. So teeth per inch. If you were to flatten the gear out, and you counted the teeth per inch, that's what this pitch or gear module is. So for any gear to mesh with another one, the diametral pitch of each gear must be the same. So for instance, if this is gear 1 and this is gear 2, then the number of teeth of 1 divided by pi times the diameter of 1, this is the circumference if you didn't know, must be equal to the same ratio for the other gear, and that's the diametral pitch. So both of these are equal to p. So as you can see in this one, the p for 1 and 2 is equal, the p for 2 and 5 is equal, p for 3 and 4 is equal, the p for 6, 7, and 8 are all the same as well. That's because they need to mesh together, and if they have to mesh together, the diametral pitch has to be the same. So you may wonder why we have this pi here. I mean, it'll make p irrational, and so actually we can just cancel it out because it's on both sides of the equation. That way what we end up with is this expression here. If you rearrange it, we have the number of teeth of 1 over the number of teeth of 2 has to be equal to diameter 1 over 2. Pretty sure that this only holds for spur gears. I'm not sure if it holds for all other kinds of gears, but in this design we're going to be focusing on spur gears only, so this is the relationship that we're going to be using. And if you get this, if you manipulate this relationship back so it's N1 over D1, N2 over D2, that's what the pitch is going to be. So we're not going to consider the pi because it doesn't matter. But just know anytime that I refer to diametral pitch, gear module, or just pitch, this is what I'm talking about. So for the main thing you need to remember is that for any two meshing gears, this ratio here needs to be equal. So another challenge is the gear tooth stress. Obviously the stress of the gear, a stress coming from the transfer of torque between two gears is going to put a lot of stress on the individual teeth. So when we're designing, we need to make sure that the material choice that we pick, as well as the width of the gear and the size of it, the size of the gear is going to determine how much force is on the gear teeth. And we need to make sure all these things come together so that the gear teeth can withstand the input torque and RPM in a worst case scenario. And the worst case scenario would be if, you know, somehow we were at full speed, full torque, and then all of a sudden we were to just grab the output shaft and stop it instantly. And obviously this probably would never happen, but that would be the only case for which we would have full stresses on all of the teeth and everything. So the other thing is the gear face width. This is a challenge to design because two gears that mesh need to have the same width. You can't just have like the skinny gear here, number 3, mesh with number 8 or number 7. It's just not going to work well, just as far as design is concerned. So, and then there's some general manufacturing constraints. The diametral pitch must be integer. So this is kind of a weird constraint in my opinion, just because the diametral pitch being an integer, I mean that's just a standardization that manufacturers place. So if you want to order gears, you can't just go online and be like, I want a gear with a diametral pitch pi, 3.14159. You're only going to be able to order diametral pitches of like 1, 2, 3, 4, 5, 6, and so on. So from a manufacturing standpoint, this doesn't make a whole lot of sense to me, just because if we were to manufacture within a given accuracy, like 4 decimal places, then we could manufacture a gear that supposedly has a diametral pitch of 5. But in reality, the diametral pitch, if we measure it to a higher accuracy than we machined it to, we could see that it's, like 5.000036461, so in a sense, we should be able to machine any given decimal diametral pitch within the same accuracy as a given integer pitch. So in real life, if you were going to make these gears yourself, you could probably do it without doing integers. But for this project, we're just going to do integers, even though I don't really like it. It was what we had to do for this class project, so we're going to do it anyway. The number of teeth, obviously, it has to be an integer. You can't have, 30.2 teeth on a gear. This won't work. The gear has to be, even number of teeth all the way around. So, integer number. The center distance between gears on different shafts must be equal. This is probably one of the toughest constraints. As you can see here, the input shaft and the output shaft are collinear. Like I said earlier, this is a reverted gear train, and that is how they are designed. The counter shaft is the same distance from the output shaft as it is from the input shaft. So that means that the sum of any two meshing gears, the sum of the diameters of meshing gears divided by 2 has to be equal. So basically, look here. So the diameter 1 plus diameter 2 divided by 2 has to be equal to diameter 5 plus diameter 2 divided by 2 has to be equal to diameter 4 plus diameter 3 divided by 2 So you get the point, but on this one with the idler, it's a little bit different. So it'll be diameter of 6 plus diameter of 8 divided by 2 plus diameter of 7. And so all of that has to be, they all have to be equal because the center distance cannot change. Otherwise you would have this shaft down here tilt and your gearbox would just wouldn't work. So yeah, that's the center distance constraint. And the gear face width must adhere to this constraint. This is a manufacturing constraint again, that we are attempting to make the face width of each gear about the same. I mean, not about the same, but they need to be not so big that it's hard to get the gears to mesh together, because the greater that we make the face width, that's the more area, if you think about it from a manufacturing standpoint, more area that we have the chance to not be very precise. So if we want to be more precise, we would make smaller face widths. So we constrain that by saying that the face width for any given gear has to be between 9 divided by the pitch, the diametral pitch of the gear, and 14 divided by the diametral pitch of the gear. So, and also the gear diameter must be larger than the shaft diameter. Obviously, you can't put a, you can't put, we can't have this shaft here be bigger than gear 6, because how would that work? It just wouldn't. So that's another thing, is that when we're designing, we got to make sure that the stresses on the shaft, which we would calculate from free body diagrams and a maximum bending stress and torsion, we have to, and with a factor of safety, we could design a gear diameter that can handle the shaft loads. We have to make sure that that shaft is not bigger than any of the gears, otherwise we have to redo everything again. So the solution procedure that we're going to take in this series is we're going to use Python. So if you don't have a background in Python, just go figure it out. It's not that hard. If you have any background in any programming language, Python will be easy to pick up, so just go do it. If you want to follow along with this, you will probably need it because it's not going to be the easiest thing in the world. And so this problem is known in the math and optimization modeling world as a mixed integer nonlinear programming problem. So basically what that means is we're trying to optimize an equation, and in this case we're trying to optimize the error between our gearbox ratios and the target gearbox ratios. Like I said earlier, if we have a design target ratio of 4.1 for the forward gear ratio and 9.1 or whatever for the reverse gear ratio, then we're going to try to optimize or minimize the difference between the actual gear ratio that we have and the target. So for instance, if we have a reverse gear ratio of 9.31, then we would optimize the function, which is the difference between ours and the target. So we would have the difference 9.31 minus 9.3. So we would have 0.01 as our error, and we were trying to minimize that error for both ratios. So that's why this is an optimization problem. And it's a mixed integer optimization problem because we are wanting to design some of our variables must be integers, like the pitch and the number of teeth. And some variables are continuous, like the diameter. Doesn't matter what the diameter is, it can be irrational, it doesn't matter. The center distance can be continuous. Things like that. So, and it's a non-linear because the gear ratio equation, if we go back, this right here, this is not linear, obviously. Look at that. We have 6 variables here, that are related in a very nonlinear fashion. So we can't use a linear solver. We have to use a nonlinear solver. Additionally, we're constraining our problem. We have a center distance constraint. We have stress constraint because we don't want to exceed the stress or the ultimate strength of the material that we're manufacturing the gears from. Otherwise, it would break. So we need to make sure that is in line. We have to make sure the gear ratio targets are hit. And there was that other constraint that the face width has to be in between here, so that's another constraint. So all these are nonlinear constraints that we have to impose. So that's why we need a nonlinear solver. And someone watching this might say, why don't you just solve this by hand? Well, I don't really think that in the real world they would solve something like this by hand. Maybe get the basic idea by hand. But if you wanted to change something in the design later on, you would have to go back through the whole process of making sure all your constraints are met, and reiterating through everything, and it's just horrible. So we're going to use a computer because it's much smarter than us and we can make it do exactly what we need. So what are we going to use? We're going to use PYOMO or PYOMO. PYOMO. I don't know how it's pronounced, but PYOMO is an open source modeling language for Python, and it's based around optimization, and it was developed by people at Sandia National Labs in Albuquerque, New Mexico, which is actually where I'm from. You know, got to rep the hometown. So real smart people over there, and they created this, which basically interfaces. So we're going to build our model in PYOMO, and we're going to pass the model, our PYOMO model, to a solver. And PYOMO basically does all the in-between of interfacing with the solver so that we don't have to. So it's really nice. And so that is what we're going to use. So you can go ahead and go get this for Python. And the solver, you're going to need a solver compiled on your machine. This is separate from Python. These are going to be binary packages that you need to compile and build. If you don't know how to do that, go look it up. It's not that hard. Just go look up how to compile binaries on Mac or Linux or whatever machine operating system you're using. So the solver we're going to use is Couenne or Couenne. I don't know how this is pronounced either, but this is an open source solver from CoinOR. CoinOR is really cool. They provide a lot of different optimization solvers, different methods, convex, non-convex, objective functions, nonlinear constraints. So basically I went through and I looked at all of their different solvers, and I found the one that would make the most sense, and it's this one. It's Couenne. And that's because Couenne can handle a nonlinear objective function, which is our error between our ideal gear ratio and the actual gear ratio of our gearbox. And it can handle nonlinear constraints, multiple constraints, and mixed integers and what have you. We can bound all the variables, so we can say if we want a minimum gear teeth, we can say that we can't have less than a certain amount or more than a certain amount. So this is going to be the best solver in my opinion. There may be a better one. Someone can correct me in the comments. It doesn't really matter. This is what we're going to be used for this. So getting PYOMO and Couenne. To get PYOMO, it's pretty trivial. You just hit the command line up and just the pip install PYOMO or pip3. I'm going to be using Python 3.6 as my interpreter for this, so I used pip3. You should probably do the same if you're going to follow on character by character with what I do, because it's going to be written in Python 3, and some of the little nuances between like 2.7 and 3.6 will shine through. So use pip3 if you're going to follow along and also get Python 3. And Couenne. So for Couenne, you're going to need to compile this package, and you can do so. I'm not going to it's not the purpose of the tutorial, so you need to go to this website here and just look at how to do it yourself. You're definitely going to have problems doing it. Perhaps I'll make another video about how to get it, but it's a really kind of painful sometimes when you're compiling packages because of all the different dependencies that they need. But if you get it from here, it should have all of the dependencies prepackaged in, so you should be all good on that. So that's going to go ahead and conclude this introduction to what we're going to be doing. If you don't have a background in gears, I'm not sure why you're watching this, but if you want to follow along, go ahead and go get a deeper understanding of all this as a really brief introduction. So in the next video, I'm going to pull up my Python IDE, and we're actually going to start building the model in PYOMO. So until then, I'm out.